To finish out the semester, we have to look at a little bit of graph theory. So we're only going to be looking at section 10.1 out of chapter 10, but I would encourage you to look through some more of the information in your textbook in chapter 10 because graph theory is actually a pretty fascinating field. So what do we need to know in order to do graph theory? Well, a graph, G, consists of values V and E, where V is the set of vertices and E is the set of edges. So we have vertices and we have edges, and edges join different pairs of distinct vertices. For example, we have in this example vertex A, vertex B, vertex C, and vertex D, and we have edges AB, AD, AC, CD, and BD. So we would represent vertices with points and edges as lines joining the prescribed pair of vertices. In chapter 8, we often represented these same ideas with directed arrows, but in graph theory, an edge that connects two vertices is assumed to be bidirectional. So if we were to draw them in, the way that we talked about them when we were talking about relations in chapter 8 is we would draw an arrow going both directions. We're going to assume that every edge is bidirectional, unless we draw a line and we draw an arrow on it that says it only moves in one direction. So we can still encounter directed graphs, but it's not as common. Another difference from chapter 8 to chapter 10 here is that edges cannot loop. So remember when we were looking at reflexive relations in chapter 8, they had a loop. And what you'll notice is we don't have this loop. Those can't happen here. So we're not going to be looking at loops. So in edges and vertices must be distinct, meaning they have to be different. You can't have an edge from B back to itself. It doesn't exist. So these vertices can be written then in either order since they're bidirectional and cannot go back to themselves. So you can write it as AB or BA, AD or DA, BD or DB. So for example, vertices A and B are adjacent, so that's a new word here, are adjacent if there exists an edge that joins the two, AB. So here in our graph, A and B are adjacent, A and C are adjacent, A and D are adjacent, C and D are adjacent, and B and D are adjacent. So a subgraph, which we were going to call H, of graph G, so if we called our graph up here, we called it graph G. Let's call this graph G. If we wanted to find a subgraph H of graph G, it's formed by a subset of vertices and edges of G. So by definition, then, every vertex in H is also a vertex in G, and every edge in H is also an edge in G. So there are lots of different subgraphs we could draw. We could draw something as simple as A to C. That's a subgraph. So that subgraph, we'll call that H1. Let's do another one. What if we did A to B and A to C and C to D? That is another subgraph. We'll call that H2. We could also do, what's really cool is we could do A to B to D and connect those guys, and that's another subgraph. We'll call it H3. There's a bunch of different subgraphs that you could draw of graph G. The other special type of graph that we might encounter is called a complete graph. Complete graphs look really, really cool because what they are graphs in which every vertex is connected to every other vertex. So this is a complete graph on n vertices, and we denote those with k sub n. So a K2 graph, as you can see here, has 2 vertices and 1 edge, and they're both connected. K3 has 3 vertices and 1, 2, 3 edges, and every vertex is connected to each other. So those are the easy ones. Starts to get more complicated once we hit K4. K4 has 4 vertices, and then we're connecting, here, if we label these, here we'll label them A, B, C, and D. We have then an edge from A to B, A to C, and A to D, B to A, B to D, B to C, C to A, C to B, C to D, D to A, D to C, D to B. So it looks like a square with an X in the middle. And then we get to a K5. Now this one looks like a star inside of a pentagon. So it's kind of cool. If you look up some of the other K6, K7, they get really complicated really, really fast. But if we look at this graph, we've got A to B, A to C, A to D, A to E, B to A, C, D, and E, C to A, B, D, E, D to A, B, C, and E, and E to A, B, C, and D. Let's continue to build our vocabulary of graph theory. So let's talk about trails, circuits, walks, and paths. A walk in a graph, there we go. A walk in a graph is a sequence of traversed adjacent vertices and edges, V0, E1, V2, E2, all the way out to Vn sub n sub minus 1, E sub n, V sub n. And it represents a walk from vertex V0 to vertex Vn via the E1 to En edges. And a lot of this will make a little more sense when we look at an example. So it's just describing how we can walk from one vertex to another and which edges we use. A walk with no repeated vertices is a path. So notice it didn't say anything about edges, it just said vertices. So a walk with no repeated vertices is a path. A walk with no repeated edges is a trail. And a circuit is a closed trail, meaning that we close the circuit, which means we begin and end in the same place. A simple circuit, then, is a circuit that does not have any repeated vertices except for the first and last. So what does this look like in an example problem? Well, let's have a look at this graph here. It looks fairly complicated, but we're going to have a look at it. We're going to look at a few different walks and see which ones represent trails, paths, circuits, or simple circuits. So let's start with the first one. It says I'm going from V1 via E1 to V2. From V2, I'm going to V3 via E3. Then I'm using E4 to come back to V3, meaning I've just repeated V3. And then I'm using E5 to go to V4. So I went like this, circled around, and came across. So we have no repeated edges. And we do have a repeated vertex. And it's not a circuit. Right? We didn't start and end in the same place, so it's not a circuit. So this walk, since it has a repeated vertex but does not have a repeated edge, we call this a trail from V1 to V4. So this is a trail from V1 to V4. Let's try a different one. Let's try looking at edges E1, 2, 3, 5, 5, 6. Well, we can't go from V1 to V2 using E1 and then back to V1 using E2 because next we have to use E3. So really we have to start at 2, use E1 to come back to V1, then E2 to get back to V2. So we've already repeated a vertex. And we're using E3, then E5, coming back to V3 via E5. So we repeated an edge now, and then down to V5. So what this walk represents is we have repeated vertices. I think it happens twice, and we have a repeated edge. And it is not a circuit. So it doesn't begin and end in the same vertex. So this one is just simply a walk from V1 to V5. It's just a particular walk from V1 to V5. It cannot be a trail because it has a repeated edge. Can't be a path, can't be a trail, can't be a circuit, and therefore not a simple circuit. Let's see if we can make this a little smaller so we can fit the rest of these on here at the same time. So, how about C? Let's look at C. C says I want to do V2, 3, 4, 5, 3, 6, 2. It's a whole bunch of vertices. So let's start at V2. Go to V3, V4, 5, 6, 2. Oops, I skipped a D. I meant, sorry, 2, 3, 4, 5, 3, 6, 2. So we did one of these guys. So we repeated V3 again. So we have a repeated vertex, but no repeated edges. And we began and ended in the same place. So it is a circuit. So we know that. So we know we've got a circuit. But because we have a repeated vertex, it cannot be a simple circuit. So it's just a circuit, right? So it's not a simple circuit because of the repeated vertex, which I believe was V3. But the next one we're going to find out in D is a simple circuit because we're going to do the same style of circuit here. We're going to start at 2, 3, 4, 5, 6, and back to 2. So we're looking at a sort of looks like a house on its side. So for this one, we have no repeated vertices except for the beginning and end, right? Except for beginning and end. So beginning and end, there we go. And no repeated edges. And it is a circuit. So this one is a simple circuit. Let's try one more. Well, actually, we have two more. Let's look at V1 using E1 to go to V2, and then using E1 to come back to V1. I mean, you just went from E1 to V2 and back is all you really did on this one. So you have a repeated edge, right, that E1, and the only repeated vertex is the beginning end, right? So I think we're okay there to say we don't have a repeated edge, or sorry, repeated vertex, except the beginning and the end. So it can't be a circuit because we have a repeated edge. So we have to call this one just a closed walk. So this one we're just going to call a closed walk. Again, because you can't have a repeated edge in a circuit, so we're going to call it something called a closed walk. So the last one is simply stating vertex V1. Well, there are no repeated vertices or edges, but there are also no edge. So there are no edges. Okay, so it can't be a circuit then. So that doesn't really work. So I think all we can really call this one is a closed walk. We're going to call this one a closed walk from V1 to V1. I think we could probably also call this a trail from V1 to V1, but that seems sort of picky. Moving on to some special types of graphs that we might look at. Our first one is an Euler circuit. So there are special classes of trails and circuits where every edge in the graph is used in the trail or circuit. Notice I didn't say anything about the vertices, but every edge is used, which kind of implies we have to use all the vertices. So if every edge in the graph is used in the trail or circuit, we call that an Euler trail or circuit. And we have a theorem to help us quickly identify whether or not a graph has an Euler circuit. But before we can state that theorem, we need to know a few more definitions. So let's start with degree. The degree of a vertex is the number of edges incident to the vertex, meaning how many edges come into or out of that vertex. How many are touching the indicated vertex. In fact, the sum of the degrees of all the vertices of any graph is equal to twice the number of edges in the graph. And as a corollary of this property, you notice that means it's an even number. We note that the number of vertices with odd degrees has to be even because an even times an odd is an even, but an odd times an odd is an odd. So in order to keep it even, we need an even number of odd vertices, or vertices with odd degrees. So now that we have a little more information, we can use this concept of degrees of a vertex to develop a really quick method of identifying if a graph has an Euler circuit. So a graph possessing an Euler circuit will have an even degree at each vertex, since each time the circuit passes through a vertex, it uses two edges. If a graph has any vertex with an odd degree, the graph does not contain an Euler circuit. So if you can find one vertex that has an odd degree or has an odd number of lines coming out of it, edges coming from it, then it cannot have an Euler circuit. So let's look at this graph that I gave you and see if we can have an Euler circuit. Whoops, I think I wrote cycle because that's how I learned it instead of circuit, but here we go. Sorry, that's a typo. So can this graph have an Euler circuit? Well, let's see here. This guy, C, has a degree of 2. So does I. So does N, O, B, A, G, and M. D has 1, 2, 3, 4. E has 1, 2, 3, 4. K has 1, 2, 3, 4. J has 1, 2, 3, 4. F has 2. L has 2. And H has 1, 2, 3, 4. In fact, absolutely, every vertex has even degrees. So yes, so absolutely yes. Yes, this graph has an Euler circuit. Or well, can have, let's say that. It can have an Euler circuit. So let's see if we can find an Euler circuit here. In fact, there are quite a number of them. You just have to be careful where you start. So I think I'm going to start at A. So if I start at A, here, how about this? I'll highlight it so we can see. So I'm going to go from A to D, and then D to C, to I to J. And I'm going to come down to N, O, back to K. And remember, with an Euler circuit, I just need to include every edge. It doesn't say that I cannot repeat the vertices. So I can go back from K to J, up to D, over to E, back down to K, come across L to H, grab this triangle, up to F, over to E, up to B, and finish at A. So the path I took was E to D to C to I to J to N to O to K, back to J to D to E to K to L, H, M, G, H, F, E, B, A. So there are a number of ways you can accomplish the same thing. If we change to a different color, and let's say we started at G. Right, let me see here. Whoops, that was the wrong thing. There we go. Let's see here. We'll go this way. We can go down, around. Let's see here. We can do this. Come up around. Come around here. Come back down, around, and there we go again. So that was a completely different circuit, but still an Euler circuit. The last topic we're going to cover in this section is that about Hamilton circuits. So a Hamilton circuit, which is sometimes called a Hamiltonian circuit, is a circuit in which every vertex is used. So unlike Euler circuits, which could repeat vertices but not edges, the Hamilton circuit cannot repeat either, but we are no longer required to use every edge. So we had an easy way to determine if a graph contained an Euler circuit. We don't have that for a Hamilton circuit or a Hamilton path. So while there's no easy method of determining if a graph contains a Hamilton circuit, there are some rules that can help. Rule 1 says if a vertex has degree 2, both of the edges incident to the vertex must be part of any Hamilton circuit. So any two edges any vertex that has a degree of 2 has to be used. No proper subcircuit, which is a circuit not containing all vertices, can be formed when building a Hamilton circuit. So you can't build a proper subcircuit. So once the Hamilton circuit is required to use 2 edges at a vertex, all the other unused edges that are incident to that vertex must be removed from consideration. So if I use 2, I can no longer use any other one because that means I'm coming back to that vertex. So once I use it, I'm done. So where that gets tricky is here with a couple of the examples we've got here. So if we look at example A, does it have a Hamilton circuit? Well, rule 1 says if a vertex has degree 2, both edges must be part of any Hamilton circuit. Well, literally every vertex in that graph has degree 2, so every vertex has to be used. So let's see if we can build one. One, we'll go up here, come down, come here, and go back. We literally used each edge once, and we used each vertex once. So yes, this one has a Hamilton circuit. So a Hamilton circuit exists. And the one we did, I think I did A to E to B to D to C and back to A. There are other ways you could do it. You could also do A to C to D to B to E to A, right? There are a couple of different ways you could start at any vertex, and as long as you traverse the entire path, you're good. But what happens when we look at graph B here? So it's going to get interesting because we don't have any vertex that has a degree 2 outside of the star, right? And even inside of the star, all of these have a degree of 3. So what happens is once we start trying to draw our Hamilton circuit, let's see here, well then from there, we either have to choose to go from A to B or to F, and then we cannot use the other side. So let's see here, let's say we choose F. Well, now this side no longer exists to us. So let's keep going. Okay, from F we can either go to I or to H. Let's see here. Let's maybe go to H, which now means, of course, we now can't use this side. Let's see here, from H, if I go to J, I'll get back to E, but I didn't use every vertex, so that's not going to work. So maybe we go to C. But now we've just eliminated this vertex. Okay, so now from C, we need to catch B, so let's go up to B. All right, but now we've eliminated this vertex. From B, we'll go to G, because that's our only option now. From G, we have to go to either J or to I. And either way, we're still going to miss a vertex, because if we go to I, then we'll have to go to D and up to E, but we have missed J. Versus if we go to J, our only option is to go to E, and we've missed D. So you'll find that if you follow the rules and you don't repeat any of these vertices, there is no Hamilton circuit here. There's no way to build a Hamilton circuit for this graph, because no matter what you do, you're going to repeat a vertex in order to catch them all. Otherwise, you're going to skip one no matter what way you go. And then for our last example, we've got this cool bow tie looking example. And this one should be actually the easiest of all three to see how you can't have a Hamilton circuit, because if I start at B and I go to E, I go to C, well, I can keep going to A, that's okay, to D, but then I have to go back through C in order to get to B. So no matter what I do, I have to go through C more than once. So there is no Hamilton circuit for this graph either. So I would suggest trying some of the problems in the textbook and then looking at and trying the online homework. if you get stuck on these problems, we can certainly look at a few of them on Wednesday before we review for the final when we meet on Zoom.